Agrawal is Assistant Professor in Civil Engineering Department, Sandipani Technical Campus, Latur. Today's topic is Macauly's method. Learning outcomes. After watching this video, student will be able to understand the concept of Macauly's method, and also student will be able to find the slope and deflection of determinate structures. The key points of Macauly's method. The first one is single bending moment equation is written which is valid for entire length of the beam in spite of the discontinuity of loading. Second point, constant of integration is written in first section since it is applicable to all points. Integration of in bracket x minus a is written as x minus a in bracket square by 2, and the last one in bracket x minus a is equal to 0 if it is the negative. Now we take here some simply supported beam and we elaborate the process. Now this is simply supported beam. Suppose this load is W1, then this load is W2, and suppose this load is W3. This distance is suppose is A, then this distance is B, this distance is suppose is the C, and total length is the L. A and the B. So now, as per the equation of this slope deflection curvature that we know, EI d2y by dx square is equal to the mx. Now this equation is used to find the deflection by the Macauly's method. Now here, how to write the single bending moment equation though there is a change of the loading. For that, here we have to break this beam into the different section. Now here this A is a reaction RA, and here the reaction is the RB. So here after this load, in between this load we have to make one section. So this is called as section 1-1, and this is the x distance. In case of the Macauly's method, we have to write the bending moment equation generally from the left side. Start the bending moment equation from the left support and complete towards the right. So now for the first section, this x is here, then here from W1 here W2. So again make the second section. We have to, because here change of the loading. So this is section number 2. Again this is our the x. So now for first here, for the section 1-1, for the section 1-1, the mx is equal to, for the section 1-1, the mx is equal to what? RA into the x. RA into the x. Now, and this is valid for x is less than or equal to the A. Now for the section 2-2, again the mx is equal to, now here this section number 2. So now again this RA into this X. Then here remaining is what? W1 load. So W1 we want here this distance. We want here this distance. So this will be this total is the X. This is the X and this distance is A. So this distance will be the what? X minus A. So we can say that due to this W1 is the hogging bending moment, that is why is minus W1 into X minus A. But this is valid for this X is greater than the X and less than or equal to the B. Then again make a third section here, because again here the change of the loading. So third section here, section number 3. Again this is our X now. Suppose this is the X. So again what? For the here the equation is section 3 then mx is equal to, again here we are writing for this section the bending moment equation. So this again RA into the X then minus here for this W1 load this X minus the A. This distance is the A. We want this distance. No. So this will be the X minus A. So W1 into X minus A, as it is the previous equation. Now this loading here W2. So this create the hogging bending moment, this is minus. Now we want this distance. So this distance is now total is the X from A to this section 3 is the X and A to the W2 is the B. This B. This distance is the B. So we want this remaining distance, that is the X minus B. So W2 into X minus B. And this is valid for, this is the valid for B. This is valid for the B less than X is greater than B and less than or equal to the C. Less than or equal to the C. Then make a section number the 3 here. 4. Section number 4. Again here there is a load from the section 3 and the B. Again there is a load, that is why again make the section 4. So again this distance is X now. So again the section 4. So mx is equal to, again this is X. So this RA into the X. Then this W1. So this total is a x, from this is the total x, and here is a, we want w1 to this distance, that is a x minus the a, this w1 into x minus a. In the same way is w2 into x minus b. Then this w3 for this is minus w3 into, we want this distance here, so total from this end to a is x, and from a to w3 is the c, so we can say that is x minus this. So this is the bending moment equation for section 1, section 2, section 3, and this is the total section x. This is a section 4 is a bending moment equation for the throughout the beam. So now here EI d2y by dx square is equal to, now we have to make the section. So first section is, this first section is RA into the x. So then make the section. Then second is minus w1 into x minus a. This is section 2. This section 2 is end here. Then minus w2 into x minus b. Then this is section number 3. Section number 1, if you look this equation, total equation, this section 1, this section 2, this section 3, this section 3, and this last section is 4. Then last is minus w3 into x minus c. So in this way we have written the bending moment equation, but make a section. So now then next step in the Macauly's method is integrate both sides. So this becomes EI dy by dx is equal to, here we can say that is RA into x square by the 2, and here we have to add the one constant of integration, but as per the key point we have seen there, always add the constant of integration in the first section. So here add one c1, which is a constant of integration, then minus w1 into, we know here x minus a, integration is x minus a bracket square by 2. Then the third section minus w2 into x minus b bracket square divided by 2. Then the last section here minus w3 into x minus c bracket square divided by 2. So this is our equation number 1. This is a slope equation. This is called as the slope equation. Then again integrate this. This is called as, this is a slope equation. Now again integrate both sides. what will happen? Again, we have to integrate this equation. So this becomes EIY is equal to, now integrate this again. So this becomes RA into, this becomes x cube by 3. 3 into 2 is a 6, plus integration of C1 is a constant. Integration of this C1 is a constant of integration. This C1 is a constant of integration. So integration of this C1 is C1 into x. Now again we are integrating second time. So add here again, once again the constant of integration. But add this only in the first section. Only in the first section. Then minus W1 into x minus a bracket cube 3 into 2. This bracket cube is divided by 3. 3 and previous 2 becomes the 6. Then the next section minus W2 into x minus b bracket cube divided by 3, and here is a 2. So it becomes a 6. Then again the next section here, it is minus W3 x minus c bracket cube divided by 3, and this 2, that becomes the 6. So this is equation number 2, and this is called as deflection equation. This is called as deflection equation. Now here in both equation, this first one and the second one, unknown is only this constant of integration C1, and here C1 and the C2. So we have to find out this constant of integration. So here the C1 and C2 is the constant of integration. Constant of integration. And these two values are calculated. These two values are calculated by applying boundary condition. Boundary condition. Now, for simply supported, now for this case, for simply supported beam, we know that for the simply supported beam here, so this second equation is a deflection equation and first one is a slope equation. So from the simply supported this, we know that at the support A here, we know this deflection, that is y, is the 0 because it's a support. Also here is a x is equal to the 0. X equal to 0, so y equal to 0. Again at support B, at here this end, we know if x is equal to the L, when we put the x equal to L, we know y is equal to the 0. Y is equal to 0. So you have to apply these two conditions for the simply supported beam. First condition is x is equal to 0, y is equal to 0, and put this in deflection equation. So we get here the C2. because when you put here in this equation x equal to 0 means only we have to use the up to first section, because limit of first section is x is less than or equal to a. So when x equal to 0, we have to use only the first section. So 0, 0. So we got here the value of the C2. Then second condition, x is equal to L, y is equal to 0. So again put this equation, put this in deflection equation. So we get here the C1 value. So in that case, when you put x equal to the L, when we put the x is equal to the L, it means we have to use all the section 1, 2, 3 and the 4, because here x is equal to L means this is a whole span. So we have to use the whole equation and find the value of the C1. Now for the cantilever beam, now if the beam is cantilever, in that case, so here is our x, anywhere is a section, suppose. So x is from the left side. So in that case, we know here at fixed support, slope and deflection are 0, are the 0 term is important here. So at the fixed support, add these here. So in this case, x is equal to 0. First condition is dy by dx is equal to 0, and second condition is x again equal to 0, y is equal to 0. So by putting this value in first equation, put this in slope equation, because here dy by dx is a slope, then y is a deflection. So put this in deflection equation. So once we got the value of the C1 and the C2, so put the value of C1 and C2 in this both equation here, in C1 here and C1 and C2 here, then we can find anywhere the slope and anywhere the deflection. This is the concept of Macauly's method. Thank you.